They packed an awful lot of information into chapter 5. As a matter of fact, if I were to make a list of, say, like the top 25 ideas, the top 25 terms that you need to know before the AP test, there are two of them here in chapter 5 alone. Okay, we're going to talk about a normal model or normal distribution. We're going to talk a little bit about standard deviation, but the other big thing here, I would say, is something called a z-score. So let's get into it. In the most recently completed Olympic Games, um, this person right here won the heptathlon. Okay, but now again we get into, oh, let's dive right into the controversy. Why do men have a decathlon, which is 10 events, but the women have something that's only 7? Aren't they tough enough? Aren't they strong enough? Yeah, go ahead and debate amongst yourselves. I'll wait. No, seriously, I won't. The 7 events, no, they're listed right there. I'm not going to embarrass you by making you quote them. They do a 200-meter run and 800 meters. The very first event that they ran in the Tokyo Games was the 100-meter high hurdles. Yeah, that's an easy one to start with. They also do shot put, yay, throw a spear, javelin, high jump, and long jump. Um, this woman, Nafi, I think is the nickname she goes by, from Belgium, won the gold medal in 2016, and she defended her gold medal. First time that somebody had done that, I think, since an American back in, you guessed it, 1988. Man, that's a long time. So if we use some of these values here from the 2016 Olympics, Nafi won the long jump when she soared 6.58 meters. If I'm remembering this correctly, in Tokyo, I think she actually beat that. I think she went like 6.6 or maybe 6.62. There was a woman from Great Britain who came in first in the 200-meter run with a time of 23.26 seconds. So, which one was more impressive? How can you compare that? Um, if you're talking about long jump, we're measuring distance. If you're talking about a run, that's measured in seconds. How do you compare things that are so very, very different? Oh, by the way, yeah, the picture that you see there that I copied, the 800 meters is the last of the 7 events that they run. They actually have some mercy on them, and they do these over 2 different days. But yeah, after you've competed, you've done your best in all of those things, they save the 800-meter run for last. So yes, all the women, best athletes in the world, are just dead tired, and they're all just sitting on the track because they're so exhausted. Um, so, how do you compare such very different measurements? We're going to use standard deviation, well, the way they phrase it here, as a ruler. It tells us how the whole collection of values varies. So we're going to come up with something that we call z-scores. You will see this frequently here. These are all also called standardized values. So our lovely little formula here, this is part of the learning of statistics. We have our own uses of variables. Get used to it. In this case, they're using the plain old y as a particular data value. The y with the little segment across the top of it here, this is called y bar. This is the mean. And the S down at the bottom, yes, you guessed it, that's the standard deviation. So for any particular piece of information, part of a larger data set, we should be able to figure out what the z-score is simply by taking that value, subtract the mean, divide by the standard deviation. These have no units of measurement, okay? So don't say that the z-score is 2.3 meters or negative 5.6 seconds, okay? So a positive z-score means that that particular value was above the mean. A negative z-score tells us that that data value is below the mean. Yeah, we don't have to worry so much about units of measurement. We just said that. We can use this as a way of comparing different scales, different units, different populations. Z-scores are amazingly useful. Countless times. I'm not sure if that was supposed to be a math pun. Countless times. Anyway. All right. So shifting data. Make sure you follow along with this. It's not too tough. If we add or subtract a constant amount to each value, then it's going to move the mean by the exact same thing. Okay, so figure out what your exam scores are, and then I try and do what some people call a curve by adding 5 points to everybody's score. Then the class mean is going to go up by 5 points. Okay, going to be true for the median and other measures of position too. Adding a constant to every data value adds the same constant of measures in center and percentiles. But if everything's moving together the exact same distance, the spread remains unchanged. Okay. So they have a lovely histogram here, actual weights of a group of men. Um, yeah, all right, fine. And then if the recommended weight for this age group happens to be 74 kilograms. Kilograms? What country was this? We can shift everything by subtracting the 74 kilograms and come up. The graphs on the right are showing how many kilograms above the recommended weight they are. What happened to the shape of the graph? Nothing. What happened to the distribution? Nothing. What happened to the center? Okay, the center moved. Okay, so by shifting the data either left or right, really doesn't matter here, should not affect the shape. It should not affect the spread. It's only going to affect the center. And again, we can figure out the interquartile range. All right, so over here, we're going from 50 to, what is that? So this is 50s, 60s, 70s, 80s, 90s, 100, 110, 120. So between 50 and 120, so a range of about 70. Here we're going from negative 20. It's the same exact interquartile range. Okay? The spread is not going to change. It's the center. When we divide or multiply, all right, now this is going to mess with things in a very different way. When we divide or multiply all the data values by some constant, median, mean, percentiles are all divided and multiplied by that same constant, but this time the spread gets messed up too. Okay? So the interquartile range, the standard deviation, those are all going to be affected by that same constant value. Okay, that's called rescaling it. The men's weight data set measured in kilograms. Okay, let's convert everything into pounds. That would mean taking each value in that data set and multiplying it by 2.2. Here's our new improved question mark distribution. What changed? Pretty much everything. Okay, the center changed. The shape of the distribution, nah. I mean, it's still unimodal. To me, it still looks, it's like it's a bit skewed to the right, but maybe not so much. But once we actually calculate either median or mean, we calculate the standard deviation or the interquartile range, those are all going to be different. Oh, look, here are the actual numbers. So the interquartile range when we measured things in kilograms was 25. Multiply that by 2.2, round that up, about 55 now. The standard deviation gets multiplied by the 2.2. The maximum, everything gets multiplied by that exact same scale factor. Okay, back to z-scores here. Standardizing into z-scores does not change the shape. Standardizing into z-scores will change the center by making the mean equal to 0. Standardizing the z-scores is going to change the spread by making the standard deviation equal to 1. Then we can compare all of that data there of the athletes in the heptathlon in their long jump and their 200-meter times. We can do a fair comparison then between things that are very different and even things that are only a little bit different. A data value that is equal to the mean, it's going to have a z-score of 0. Okay, so again, remember we're taking y minus y bar, and if you've got those two numbers the same, it really doesn't matter what your standard deviation is, your z-score is going to be 0. Okay? If we have a z-score of positive 1, exactly 1, that means that value in our data set is exactly 1 standard deviation above the mean. If we get a z-score of -1, that means that value is exactly 1 standard deviation below the mean. So a z-score is giving us a way of measuring how unusual a value is, because it's giving us this new scaled score of how far is it from the mean when, be careful, our scale here is measured in standard deviations. A z-score will tell us how many standard deviations that one data point is from the mean. Yeah, we really don't have standards in statistics. How far from the mean does that value have to be before we consider it interesting or unusual? Um, yeah, anything that's 2 standard deviations away should draw our attention, but every data set is different, so we're going to consider things in context. Okay. Again, negative z-score, it's below the mean. Positive z-score, it's above the mean. If you forget in what order subtract, use common sense. Is this point above or below the mean? If it's below the mean, you should be getting a negative z-score. Okay, so let's keep that in mind. All right, then how does this apply to the normal model? Okay, you've heard of a bell-shaped curve. Um, yeah, your calculator is programmed to do this because it's amazingly useful. So many things you will find out as we're going through here can be approximated by a normal model. Now, I don't throw that word approximated out lightly. No data set that you're going to find is ever going to fit the normal model perfectly. If you show me something that fits it perfectly, I'm going to be extremely skeptical. That's not the way the real world works. You find me something that fits perfectly, I'm thinking the data has been doctored. So we're going to find things here that fit an approximately normal model. And that approximately is a very important word to make sure that you include. All right, a little bit of Greek here. They're going to use this notation. This first one here is the Greek letter mu, and that's what we're going to use for mean. The second one here is the lowercase letter sigma, and that's what we're going to use for standard deviation. Okay, so get used to seeing it written in that form. Um, yeah, such numbers are called parameters of the model. Yeah, we should know that. All right, so another way of looking at a z-score, we're going to take a particular value and subtract mu, the mean, and we're going to divide by the standard deviation, sigma. Okay, so our standard normal model is going to be written there with, again, the n, 0, comma 1. So our mean is going to be 0, and our standard deviation is 1. We're going to talk more. We're going to see, we're going to look closer at some data sets and talk about, is it approximately normal, or is there something messed up with it that we can't use the normal model? But we'll get there now. If the shape of the distribution is unimodal and it's roughly symmetric, we'll say it's close enough that we can approximate things. All right, this is, I think, the last part we're going to go through here. For this, you need to know, you need to be familiar with, and you need to be able to recall this pretty quickly, the 68, 95, 99.7 rule. So if we have something that's approximately a normal model, about 68% of the values are going to be within one standard deviation of the mean. That means plus or minus. Okay, so if you look at these down here at the bottom, the value here for mu plus sigma, so that's one standard deviation above the mean, and mu minus sigma, one standard deviation below the mean, that should encompass about 68% of our data in a normal model. If we go two standard deviations, so mu plus 2 sigma, mu minus 2 sigma, that's about 95% of the data. And if we go all the way out to 3 standard deviations, that should encompass about 99.7%. So again, the 68, 95, 99.7 rule. No, it's not nearly as eloquent. It does not roll off the tongue like the 30, 60, 90. You'll get used to it. So again, 2 standard deviations, which should give us about 95% of the data. 3 standard deviations, it's virtually everything. Now again, I don't know if you pay attention. I don't even know if you look at these things. Do you ever look at the page on portals for this class? I mean, not the grade book, but the actual page here. Evidently, I don't either because this is taking a little bit to load. There we are. For D block AP statistics, yep, that's what I put in. One of the things I put in your class summary. The 68, all right, slightly different picture there. They're going just a little bit more accurately here, but again, 68, 95, 99.7 rule. Okay. Oh, by the way, have I mentioned the AP exam is scheduled for May the 5th? Okay, what are we talking about here? Another feature I like of the one that is in your notes here, it gives you then the corresponding z-scores. If you have a z-score of +1, that means it's one standard deviation above the mean. A z-score of 3 means you're 3 standard deviations above the mean, and oh my goodness, that's unusual. Okay, so you can take a closer look at that later. Make a histogram, check that nearly normal condition to make sure that we can approximate things with our normal model. All right, so let's go through things here. Below is a histogram of the heights of all Major League Baseball pitchers on opening day of 2017. Okay, lovely histogram. How would you describe that? Yes, it's unimodal. It's roughly symmetric. We could approximate this with a normal model. Okay, then they give us some more interesting numbers to crunch here. The mean height of the pitchers is about 74.5 inches, standard deviation of about 2.1 inches. What proportion of baseball's pitchers would we expect to be at least 78 inches tall? All right, so we need to, again, check our nearly normal condition. Yeah, that seems reasonable. So then we can model their heights using a normal model there where 74.5 comma 2.1 is what you might type into your calculator. We'll go through that in just a moment. All right, so if we try and make a picture here of this normal model, all right, so we know that the center of it should be at 74.5. So that's where we're putting this high point on our graph. How high or how low your graph goes, it really doesn't matter because you'll notice here that for a normal model, you are never going to see anything over here on the left. You're never going to see any kind of a scale here if we're just drawing the normal. So again, if we know the standard deviation is 2.1, all right, so from the 74.5, if we add 2.1, that means I should go out to 76.6 for my first standard deviation. I should go another 2.1, so that should give me 78.7 as my second standard deviation, and another 2.1, so that'll give me 80.8 as my third standard deviation, where it dips down here. So it's almost, not quite, again, 99.7 isn't everything. So it's really, really close to getting down to 0. Okay. And then I would do the same thing on the other side. Subtract 2.1 over and over so I can get a sense here of 72.4. So again, between those values, that's where 68% of the data should be. Okay, so once you get used to this, subtract another 2.1, so 70.3. Subtract another 2.1, so you're thinking about, getting those to be roughly in that shape. Okay, and again, the graphs don't have to be absolutely 100% perfect, but you do need a consistent scale down at the bottom. Okay. Again, think of this as you're going to plot those points on a number line where things are evenly spaced, and then you're going to draw that normal curve. All right, so let's do the calculations of the z-score. Again, somebody who's 78 inches tall, so we'll take the 78, subtract mu, the mean of 74.5, and then divide that by 2.1. So we will get a z-score of 1.67. Okay? So is that unusual? All right. Well, again, the z-score tells us how many standard deviations we are from the mean. Yeah, it's more than one standard deviation, not quite two. Yeah, that's going to be unusual. Now it says here they just give you the generic use technology. and find that the area to the right of 1.67 under the standard normal model. Yeah, okay. How do we do that? Yay! This will be the last thing that we do here. So if you take calculators, again, if you're just in the notepad there, that'll work. Push the menu button there, and hey, what do you know? We're doing 6 statistics. From that menu, we're looking at option number 5 there for distributions. And from that, then we're going to go down to not number 1, but do number 2, the cumulative distribution function. Okay, option number 2, the normal cumulative distribution function. And okay, what percentage of scores are less than a z-score of 1.2? Now, the default setting here initially is negative infinity. We're going to leave that to answer this particular question. Okay. And we want to know what percentage of the scores are less than a z-score of 1.2. So we'll go and type in 1.2 in the upper bound, leave the mu as 0, leave the sigma as 1. We're not going to mess around with those unless absolutely necessary. Let the calculator figure things out here using our standard normal curve. So just tab, 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 get down to the OK and hit enter. And then what'll show up then on your calculation screen is our normal cumulative distribution function from negative infinity to 1.2 with mu of 0, sigma of 1, about 88% of the scores are going to be less than a z-score of 1.2. So that gives you the percentage to the left. Now, if you think about going back to that normal graph there, if we figure out where 1.2 is on here, and we want to know how much of the scores are less than that, we're asking the calculator to compute all of this area here. All right, well, that's quite a bit of it. Okay, not quite 2 standard deviations, but it's all of this stuff there to the left. All right, about 88% of it. What percent of scores are above a z-score of 2.7? So now 2.7 is our lower bound. We can type in infinity. If you can find that button on your calculator there, that's great. A lot of times I don't mess around with it. I know, again, a z-score of 3 puts you at the very edge of the graph. So a lot of times here, I don't want to go looking for the infinity. I'm just going to pick a really big z-score like 10. Now you notice here what happened. I did this twice. The lower bound of 2.7, the upper bound of infinity from the calculator there, I got 0.00346702,305. If I got lazy and I didn't want to go looking for the infinity, I went again, lower bound of 2.7, and I put the upper bound with a z-score of 10. 10 standard deviations above the mean. In that case, I got 0.00346702,305. It's the exact same number. 11 decimal places, it's the exact same value. So if you know where the infinity button is and you want to use that, that's great. You don't need to use that, okay? Oh, and then yes, I will torture you with this next time about finding normal percentages by hand. But if you can understand how to use the calculator here, oh my goodness, it's so fast and will answer so many different questions. So that's where we're going to quit. If you take a look at OneNote, I've given you Chapter 5, Assignment Part 1, and the answers to those problems. We'll pick up where we left off here next time, and then there will be a Chapter 5, Assignment Part 2, again with those answers. I want you to go through and try those. Try using your calculators. We'll get back together, answer any questions that you have. So very important to understand the concepts here in chapter 5. I don't want to rush through it. So that's all for this time. Use your time wisely that remains here in class, and I'll see you guys later.